Hello, I'm Roger Bisbee from the Skill Builder channel, and I'm delighted to say that we're joined by Harry Rear from Cork in Ireland. Now, Harry has been in touch with us because he's got a few views on the heating industry and the way that things are done, and particularly about heat pumps and solid fuel. So I love your background, by the way. Is that your handiwork or somebody else's?
Yeah, that's one of our systems, where I say, but it's a very interesting because it was a 27,000 square foot house.
Oh,
and we had two old oil boilers, and they had a really, really bad boiler house. But now we put in a spare 100 kilowatt boiler, two working 100 kilowatt boilers. And then we also have, we have three heat pumps, which you might see just behind my back here, three 20 kilowatt heat pumps. And we basically put in the two boilers thinking that would be what would be needed for the house, because it's an old house with, some of the walls are 4 foot thick, 3 foot thick. But we actually found when the job was finished, the three 20 kilowatt heat pumps are heating the building.
Without the boilers even kicking in?
Well, they do kick in when they absolutely have to, but we've designed the system so that the boilers will only kick in if they're absolutely needed. What we have is a little control center, and we have three different ways, but the one we typically use is you connect on your heat pump, connect on your boiler, say for a standard system, connect on your boiler, connect on your heat pump, and you have 4 zones. And when a zone calls, no matter what controls you have, it times how long the zone is on. You decide, we typically find an hour. You can have 3 choices. I think it's 30 minutes, 60 minutes, 90 minutes. If the time passes and any zone hasn't come up to temperature, it switches over to the oil boiler or gas boiler or whatever you have. But you can then decide, do you want the heat pump to keep running, or do you want to turn one off and turn one on? Where on manifold, you can have the two of them running at the same time, because manifold, I can show you how it works inside, but the two waters don't mix.
Oh, really?
Just skip past for a second. We made like a prefabricated heating system. So it's a 200 litre cylinder with a very, very high recovery coil. It's also very, very high quality steel. So the steel isn't affected by well water and the like of that, and has a built-in volumizer, has built-in wiring center. But the amazing thing, it all fits in a standard hot press, like 3 foot wide or what less, and maybe 850 deep, 700 wide, that kind of way. And the entire heating system fits in there.
Really?
Except the outside heat pump. So the heat pump has to get its heat out from the boiler, And when it does, it just has to, nothing should stop that flow. If it stops the flow, the heat pump can have issues with the compressor overheating or with the refrigerant overheating, with parts going wrong. So that's why heat pump manufacturers are constantly saying you should put in buffers and you should put in volumizers and whatever. Sometimes you need a volumizer depending on the size of the system and the size of the heat pump, whatever. But normally speaking, if I have an empty box, just an iron box, and I put water in and I take water out, there's going to be very little technically to go wrong with that. If I then put in 2 plates and a large gap on the right-hand side, if a heat pump comes in from this side, it simply flows across the top of the plate, down over the gap, down to the bottom, back, and back to the heat pump. There's the heat pump's job now finished. It has nothing else to do. But when it comes in, if there's any air in the system, because the distance from here to the vent is more than 7 times the diameter of the pipe, because this chamber, the top flow chamber, is the equivalent of a 2.5-inch iron pipe. The water slows down because it's traveled, and as it travels slower, any air gets trapped here and it's immediately released. Now the hottest water coming in from the heat pump is passing on the top chamber. It's passing these pipes that take heat away to zones. So if I turn on this pump, I might heat my hot water. If I turn this pump, I'll show you this, there's a reason you wouldn't have a pump here. This would be underfloor heating. You don't need a pump on the manifold for underfloor heating. And this might be, say, a bedroom circuit heading up. But if I change it around and I put a heat pump in from this side, the heat pump can come through this pipe, ends up in the exact same place, hits this V-shaped baffle, turns back on itself and goes the exact same path and back to the boiler here. So that the complications are gone. All these things of close couple T's and trying to figure out how do you bypass valves and how do you protect the heat pump from being obstructed by controls, or where a guy doesn't fully understand what he's doing. At the same time, this is the neutral point. You couldn't have a better neutral point, because this is where you would join your expansion vessel or any spare connection. And that means because it slows the water down so completely, because your cold feed would be joined into this, whether it's an open system or a sealed system, I can categorically say that this, in your entire heating system, this is the neutral point, just here. If you think this pump is pulling water from here, it pushes it through the magnetic filter, through the heat pump, and back up and into here. When it comes back, it now satisfies its own vacuum, if you understand me. The thing that I've noticed people say, they think a pump causes pressure. It causes a differential of pressure. It takes the water from one place, puts it to B, and puts it back to A, if you understand me. So a pump doesn't... if a pump is badly located and the neutral point is moved into a wrong part of the system, then you get pitching with an open system, or you get air being drawn into a sealed system, and that's where all the hassles come from. People are getting the basics wrong. So I'm saying to you, if you were to go back to the most fundamental gravity-fed system, all the answers sit in there. And this is as basic as it gets.
So when you say this is a gravity-fed system,
if it was,
obviously it's not. But what you're saying is that if you, where the heat pump was going to go on the left-hand side of his screen, say, if that were a solid fuel boiler, for example, what you're saying is you would have exactly the same arrangement there.
No different.
You'd have it gravity. You've got no restriction on the flow. You've got nothing to stop. So is that the idea or not?
It's exactly that. It's just basically what happens. Do you know the most perfect heating system, if you think of this? If I get a barrel of water, right, and I put a pipe leaving the top of the barrel, head off around my house, and it comes back to the barrel, and I have a fire under the barrel, and I'm heating the barrel of water, and I have a pump pumping from the barrel away and around the system, and it comes into the bottom of the barrel, the fire heats it again, goes up to the top, rises away. Well, that's basically what we have. We have a container that has water in it. The water is being taken from the end of the container, is being heated by something, and comes back into the top of the container. If the container is sealed, it just means that you have an artificial volume, air container that expands and contracts as the water contracts. And if it has a tank, there's no difference between a sealed system and an open system, in that it's just somewhere for the water to expand to. But because sealed systems and let's say completed boilers coming from the manufacturer came on the market, installers forgot the basics and they just rely on the mechanical boiler to do all the thinking, if you know what I mean. Whereas if you go back to basics, you have to figure out where's the neutral point, how much water you're pumping, what size pipe are you using, how quickly is the water moving, and then are you letting the water in the boiler long enough to pick up heat, or is it so slow going through the boiler that the boiler is overheating? So you have all, with a situation like this, if the water is going through the boiler, let's say 100% of the water coming in here from a heat pump. Let's say this pump takes 33%, 34% here, 33% here. If this water comes in here and this pump takes away 33%, that means there's now 67% carries on and heads straight back to the boiler, no obstruction. If two of them, you have 33 and 34, you have 67%, 33% of the water goes back. So you're never, ever interfering with the heat pump, even though the suns are on or off, you know?
Yeah.
So anyway, the other thing I told you, if I have a barrel of water and I put a pipe leaving the top of the barrel at the side and coming back for the bottom of the barrel at the side, and if I put my pump pumping into the barrel and it's a 10-meter pump, say, in that system I have 10 meters of head pressure is between the pump and the barrel. But if I pump from the barrel out and it goes around the system, I have 10 meters of pressure all the way around the system.
I understand, Harry, because I did quite a lot of solid fuel systems in my time. I understand the principles perfectly well there. The neutral point in an open vented system is where the cold feed enters.
Yes.
What I struggle with on these systems is working out where the neutral point is and therefore where I should place the pump. Yeah, because what you're saying is that basically you want to put the whole thing under positive pressure if you can, rather than a negative pressure on the system, on the underfloor heating or the radiators. Yeah, is that right?
See, let's look at this. Say we have, forget this for a second. This is an energy link, so it takes the heat exchanger, and we have open primaries.
Yeah.
If I take this flow comes out of here, and if I was to bring that flow, there's literally an open pipe. Goes up, goes in a circle. Now, up here is interesting because we have our heating tank, our expansion,
Yeah.
the water inside. So we have a reservoir, and the water in the expansion is up to this height here, same as the height in the expansion. The cold feed should never, ever rise directly up to the tank. Most people make that mistake as well.
I do.
It heats the water in the tank, the water evaporates, fresh water comes in, everyone wonders why their system is all black. Because you're feeding oxygen into it. You have to have a heat lock. And this is a heat lock that traps the heat so it won't rise up into the tank. Within 6 inches of this, so there's no potential difference, so it doesn't pitch. You have an open expansion and you have a cold feed directly down. When the water passes down through here, it passes in through this pipe, which again is 100% open. But now there's a T taking this pump away, and we have a stat, and a stat should never, ever be on the flow. A stat should always be on the return, and 55 degrees is when it condenses. So if you put a stat on the flow, and if you start the pump at 55 degrees, you're causing condensation in the boiler.
Yeah, which is rusting the heat exchanger.
Yeah. So this stat reaches 55 degrees. It turns on both pumps. This pump pulls water out of here, down through, cross, and into the exchanger.
That's a plate heat exchanger there.
Inside here, there's an injector T. There's an elbow, and it's facing downwards. So now when that pump runs, it fires the water down the pipe and back into the boiler. There's no pump on the primaries. You should never, ever put a pump on a primary circuit. You should, because there's valves on pumps. If someone valves
sure.
This then, as the water's travelling around, if there's excess of heat left over, the heating system has taken as much as it can now, because this pump, secondary pump, there's a vent up here, look, that takes any potential air away. And the secondary pump puts it into this manifold. So therefore, you have water flowing in here again. This is the overall system's neutral point. When it gets to here, and now this is taking back the hottest water. The coldest water is coming back from the zones down to here, can be taken by the heat pump, whereas the stove can take the hot water that's left over from passing the zones. So the stove is working at a high temperature, whereas the heat pump predominantly is working on the zone return water, so that can operate away.
Basically, on that system, you've got an open vented connection on the heat pump then, haven't you?
No, the heat pump will be a sealed system. There's a pressure vessel will be put on this.
So when we come out of that, what are we calling that unit, that box, by the way?
This is the energy zone.
So if you call that the energy zone, that's fed in from the feed and expansion tank.
The open system has the expansion and cold feed.
Because you've got the plate heat exchanger in there. Okay, now I'm with it now. Okay, yeah. That plate heat exchanger is your hydraulic separation between the solid fuel boiler and the heat pump.
Correct. So this is a sealed system, this is an open system.
Yeah, got it. Okay, sorry, I was thinking it was all open vented, but it's not. Okay, yeah. All right, that's fine.
The return's coming down, and if you have excess heat and the stove has to go to turn down mode. The turn down mode of the stove is when, you probably know, when the stove is fully loaded, but the dampers are closed, what's the minimum output you can get? So your radiator up here should be that. And whereas people pipe onto the radiator, it should be an open circuit again. And then
like a heat leak, we call it, yeah.
So, but if you see it's taken from the same pipe.
Yeah.
So that water.
Oh, okay, yeah. Oh, how funny, yeah. I didn't see that, yeah.
So
I would have
you have
put
no wasted on your heat leak unless you absolutely have to.
Yeah. Oh, that's interesting, yeah. Just that little bit of differentials. How much distance would you put between those two?
Much as possible. If I could get, 2 meters, I'd take 2 meters. If it was, the least you should have is more than 150 mil.
Yeah.
But I would think, say 300 or 400 mil would work away perfectly well.
Yeah, so that's what you're after. And would you do that in 15 or 22, that bit?
22 mostly, but you could go to 28 depending on how big the stove is.
Yeah, okay. All right, I'm with it.
If this is going to be working without a pump. It has to work.
Yeah, for sure, yeah.
Oh, if you look, the hot water is tumbling down here. When it gets to here, it wants to rise. That's another thing. People think that in a primary circuit, the water wants to circulate. No, it doesn't. It just wants to, the hot water just wants to rise. But to be able to rise, it has to push the cold water that's up there, and the water falls. And so the water's trying to level out at a hot level, let's say. So this is trying to reach the top, and this is falling down. So when this is falling down, it comes to this C first, and it does what nature tells it to do. It rises. and then it goes round this loop. If it was going through a radiator valve, it has resistance. But by doing this, it has a perfect circuit. When it gets to here, it rises. When it gets to here, it falls. And now it falls into this loop, and it falls back down, and so it's 100% safe. Your expansion is exactly where it should be. Your cold feed is completely protected with a heat leak. It's by the book correct. And now, so that the solid fuel side could not be simpler and could not be easier.
Just tell me what happens if we didn't put that cold feed with that little loop, that drop loop. If you just put it like I have so many times, just straight up, that means that you've got hot water rising into the feed and expansion tank. It's going to be releasing air from the system as it goes. What's the harm in it?
The harm is that, just as I said to you, hot water wants to rise from the solid fuel boiler. Hot water wants to rise from the cold feed if it's connected to a hot pipe. It rises up the cold feed, goes in, and it's stored volume in the tank. That tank water is hotter than the air in the attic. It evaporates. The boiler lets fresh water in, and now you've got a stream of fresh water going into your heating system.
Got it. It's the evaporation. So every time I've taken the lid off a feed and expansion tank and seen droplets of water on the underside of the lid, that is because it's trying to evaporate out of that tank into the loft.
Yeah. So when you do this, there's you might remember this. It's a little trick. If you want to see if the heating system is done properly, what you do is you get a glass of water, you go to the attic, and you scoop out some of that water with your glass, stick the glass of water onto the expansion pipe, get someone to turn on and off the system. If that water moves a millimeter, something is wrong in your neutral point.
Yeah.
With this system,
it's sucking in or it's blowing out, is what you're saying. Yeah.
Whereas with this system, it doesn't budge. There's no movement in the attic. So when people are saying putting tall expansion pipes, that's 100% wrong, because it shouldn't be moving in the expansion pipe. If it's moving the expansion pipe, your system's going to rust.
That's interesting, because I've done that. Extended the expansion pipe up, the vent pipe up, if you like. Let's call it the vent pipe. Extended that up to stop the pumping over, as we call it here. What did you call it? You got another phrase for it, pumping over. Pitching, yeah. Well, just to explain to people, the pitching is when you've got water going up through that pipe there, which would be our vent pipe. It's entering the feed and expansion tank, and it's being sucked down the cold feed back into the system, and that is the worst possible scenario, because it means you're continually aerating the water, oxygenating the water, and it's rusting the system very quickly. I've been up to so many jobs in the past where that's happening, and the loft is full of steam, and people wonder why their heating bills are so high, and the radiators are rusting through. So that's a definite no-no. We got to a certain extent, a lot of these problems have been overcome. If you haven't got solid fuel, they've been overcome by the fact we've got sealed systems, haven't they? But you're still saying that sealed systems can be problematic. I'm not saying with the solid fuel, forget the solid fuel. If you just got a sealed system without the open vent, you say you can still get aeration, you can still get air coming into the system because it's drawing in, because the pump head is exceeding on the negative side of it, it's exceeding the static pressure of the system.
Well, where a lot of people make mistakes is, for example, you have a flow and return. If I just forget what's over here. I have a pump here that's actually pumping back to a boiler. But just suppose I'm trying to find the best circuit to look at. Say this one, right? I have a pump here and it's pumping up, and suppose this is going in extended distance. You get people who will put an automatic vent on the flow pipe and a vent on the return pipe. And now the vent on the return is on the suction side of the pump. And when the pump comes on at the first start, it gives a water hammer a little kick, and that'll pull in it something. If there isn't a proper valve there or an appropriate type valve, it gives a little bubble of air into the system every time. And that happens 20 times, 30 times a day. You've got a sealed system that's pulling air in, and then the automatic air vent lets it out. So it's putting air through and out and through and out. And then you open the sealed system that should be perfectly clean, and the water's all black. And you wonder why. So the trick with that is, if I can explain this now without proper diagram, if these two pipes are traveling across to go to another rad, and if I do have a vent here, I don't put a vent in return. I put a T here, and I teed the two of them together with a valve barely open. The valve is just enough to let any air that's trapped in this pipe rise up into this pipe, and then you have one vent on the positive side of the pump, and the problem is, and you have, and you know, so you can make, as I say to you, there isn't a fundamental difference at all between sealed and open systems, but you still have exactly the same issues, but they're hidden better with a sealed system.
Yeah, interesting. Yeah. When you say about water being black, I'm not worried about black water in a heating system. It's a bit of magnetite, but it's the orange water that is showing active corrosion, isn't it? Isn't that right? I mean, you wouldn't expect it to be clear, would you?
Yeah, it's basically methane. You set fire to it. But what it is organic growth within the water fed by the oxygen. But if there's no oxygen in the water, you can't have life. And the life can't cause when the oxygen is getting in as well, it attacks the ferrous parts and it's rust. Yeah.
So you've got to have when you fill a system up, you're going to have a bit of oxygen. You've got a bit of free oxygen in there, which is going to disperse and, you know, bubble out over the time as it's heated and so on. So, but you know, H2O, I mean, that's basically hydrogen and oxygen anyway, so you're always going to have oxygen in a system, aren't you? You know, so
but it's not
active
constantly. Yeah. And when the oxidization is finished with the original water, there's no chemical action that can cause more oxidization.
So would you say, I mean, the Heat Geek, they're quite interesting actually. They've got a few what I would call radical ideas, and one of them is that you don't bother putting any corrosion inhibitor in a system. They think it doesn't do anything, basically. If you've got the system designed properly and you haven't got those problems, then there's no need to put corrosion inhibitor in. So I don't know whether that's true or not. I was going to ask Fernox.
Coming to one of my kind of pet subjects. About 4 or 5 years ago, I was a member of so many different groups, and every day there was someone saying, look, if you put close couple of T's here, and if you use the pump here, and use this valve and put in a 3-port. And what they were doing was trying to figure a way to stop all these systems problems. And there were so many people objecting and said, I've done that before and it didn't work. So then someone came up with a brainwave. Why don't we just not have zones? Then we just let everything run around forever and nothing can happen. And it seems as if it worked. But the truth of the matter is I am not one of those who believe that leaving a house run forever with the boiler running forever will save you money. I believe the zones are pure common sense. In fact, every investigation of systems will say that if you turn off a zone, you're saving money. The argument is that if you turn off a zone, the COP of the heat pump will be affected when it's heating it back up. But if you look at the mathematics, the COP is being affected for a short period of time where you bring the temperature up again and then it carries on cruising as before. Whereas if you have a hybrid system, just suppose, the hybrid boiler brings up very quickly and then you go back to your heat pump and here presto you can have anything you want. But even if you've just a heat pump, you can say in some situations that it is wise to let the heat pump run forever. In a huge number of situations, it's absolute madness. I mean, the way to think about it, if you have 1,000 rooms in a hotel and there's 20% of them being occupied, will it save you money to leave the 80% on?
Yeah, absolutely. I've argued this with Adam from Heat Geeks and a number of other people. I say, look, the cheapest way to run your system is to turn it off. You know, when it's not running, you're not consuming fuel. And so if you've got heat losses from a house and you're putting the water in, you get a 50 degrees Celsius flow temperature, but you've got high heat losses from your house because you've got lots of rooms, you know, and the idea that you're putting more heat into that just to have it flowing out again when you don't need it in those rooms, to me is just madness. And I operate my house, I've got zoned upstairs and so on, so during the day we might have the downstairs operating, leave the bedrooms come on later on in the day, and even, you know, the kids can have if they're late, you know, we've on the bed and they want them on later, they can, you know, have them on later. So for me, it just makes sense and it works. Now, I know people say, let's just keep the whole thing ticking over at a nice low temperature, everything open, like you say, and you'll save money and you'll feel warmer. But I just can't, for the life of me, see how you can save money if the heat. If you've got a really well insulated house, the difference is going to be negligible probably, but the fact is that as soon as you open a door or a window or anything else in a house, you've got air changes and you're losing heat, even if it's well insulated.
But the presumption they have as well is that if you turn off a zone, that suddenly it's going to go slap down to -2 degrees outside. So what I'm saying, that the room will fit, it doesn't.
Yeah.
One of the things about you've invested money in insulation, for God's sake, let it pay for itself.
Yeah, absolutely.
Turn off the heating when you don't need it, and let the insulation maintain the heat to a certain level, and have it so that you can bring it on again so you don't notice it. If you know what I mean.
That's a very good point, because I've said that to people as well. I've said, look, if you go out to work during the day and you turn your heating off and you come back and your heating's been on for an hour before you come home, it's not starting from zero. It's starting from, you've had a heat loss through the house during the day, like you say, limited by the insulation, and all it's doing is bringing it back up from that point. It's not lost all the heat in the house. Leaving the heat pump or whatever it is you leave on all day, whether it's a boiler on a low temperature, you're just keeping pace with that heat loss, and so that when you come in, you haven't got to wait any time. But I say, if you time the boiler, you know what time you're coming home, and even if you don't nowadays, you can do it on your phone with an app, and you can switch heating on. If you're coming home a bit earlier or a bit later, you can adjust the heating accordingly. So I don't buy this constantly heating all the homes, but it seems to have been something that's caught on quite a lot. And as I say, Heat Geeks are a big fan of it, and I do get emails from people all the time saying, no, I've tried it, I've experimented, and it's cheaper to leave it on.
It depends on the house completely. And you find that people who have really well insulated house are very interested in the mathematics and study it more. But if a guy has an ordinary house, look, here's the bottom line. If you take a largish house and maybe have a living room, it might be 1.5 kilowatts. And so you're going to, will you have that on or will you have that off? If you went out in the morning and you forgot to turn off 15 100-watt bulbs when you came in the evening and you noticed you left them on, would you feel foolish? Because you just a radiator on that has 1,500 watts, which is 10 100-watt bulbs, burning for no reason. Say this is a system boiler, just suppose, and it has a pump. And the pump is pumping the water out of the system boiler, and then it comes to a motorized valve for your underfloor zone, and then you have a pump in your underfloor zone. So now, let's say this boiler's firing because another zone is calling. So now the water starts coming down from this pump, being forced, comes down here, and it comes across to here. This is cold, so it passes through this pump, goes out and heats your floor, and then it heads back to the boiler, and this pump takes in. That's fine. Then this valve starts to come up to temperature. So this pump can't now pump through here anymore. It wants to go down this pipe. Whereas this pump wants to push water up that pipe. It's fighting the pump. And now you say, people say, my floor takes ages to heat. Yeah, because the plumber made the two pumps fight each other. Whereas in this situation, you don't need a pump here. When this pump draws water, if it's taking it from that circuit, it simply pulls it down. And when it's circulating, it just circulates, and so the underfloor heats by far. It has only got its own pump action to deal with, and it doesn't contend with an aggressor coming from the other side, if you understand me.
Yeah, no, I understand. I was looking at that. I was interested in that because I thought, well, there's no pump on that circuit going up to the box, if you like, so as you would normally have. So this pump that you've got on the manifold there, which is not in the conventional place, is actually doing the whole job, isn't it? So, but it's still allowing the mix. It's still allowing a little bit of water to come back through the return from the underfloor heating circuits.
100% of the water that's needed. It doesn't restrict anything. It's actually less restrictive.
You're a system designer, basically. Yeah, you work for a company or for yourself or whatever.
I had a different manifold before. Myself, my son worked together. He's worked with me for 17 years, and we had a manifold. And then there were some issues where we had problems with directors. We ended up losing our manifold. So then, but I always had this idea in my head, and my son then suddenly came up with the idea of the second plate and using it in this way. So we tried it only on our own work. And it worked so extremely well, you couldn't believe it. And so many people were saying, that's a seriously good product. You should go into it. So we were doing that, and we were doing quite well. And then, believe it or not, an American company were doing a project in Patagonia. And they were building a dam in Patagonia, and they had to make accommodation. and we were asked, would we design the system that could be picked up, and because I was able to design it on this program, pick it up and move it on to the next part of the project and drop it, and then 300 men would live in different places, and then they have groups of 300 men. So we had to make the plumbing and heating to move. So we designed the system around this, and they were very satisfied. It worked extremely well. So then they gave us they said, do we want to join their company as the energy side? So now we do all of the energy designs for Seabox, where Seabox is a huge American company. They're particularly into containers, but they do containerized hospitals and containerized airports. We get a job to do where there's a sports complex, so we get a container, we put in very high efficiency boilers, we put in manifolds, we put in everything goes into a container, then it's brought to site, dropped down, connected on. The building management system is finished completely, and it's just done. And
That's fantastic.
The one thing about it, it sounds weird, but I'm saying this publicly, we get no complaints. We never ever get complaints. We had one or two manifolds that had silly leaks over the years, and we had just silly things, but we never ever had a system complaint, not one, which is very weird in the heating business.
Yeah. No, I'd love that. I'd love that record myself. This job in Patagonia, then, was that solid? Was that wood burners or what? What was that? What were you? This
is as ridiculous. I actually don't know where the heat was coming from. We were only told to do the distribution. I've asked that question so many times. I know we had minus 15, but I believe when they went to different places, they had different sources, so we had to make it just connections that they could connect onto whatever they were moving to.
That's interesting. So it could be a heat pump at one point, it could be solar, it could be solid fuel or whatever.
So we just made it so that it was completely transportable.
That's on my list, Patagonia. I'd love to go there. Have you been?
I'm into trout fishing. I believe the trout fishing.
Yeah, fantastic place. Not a country, an area.
Yeah, absolutely. Yeah.
Chile and Argentina, but lovely. Yeah, absolutely beautiful. Look, it's been great talking to you. I think I could quite honestly just listen to you for hours, because you've got a wealth of knowledge there. But this is absolutely beautiful graphics as well. You put these together, and that's just one of many systems you're working on, obviously. Yeah.
Well, like I say now, the two jobs we just finished with the two chemical plants, where the manifolds are about 2 meters long, 500 deep and 700 high, and they had two 650, each separate boiler house in the same building, or same area, and then they put on two 350 kilowatt heat pumps, taking air to water from up to 35, and then another heat pump taking that water up to 70, and then
I know,
ties it all together. So we do hotels, houses, cottages, doesn't matter. But you see, there's another major benefit just before I leave you. If you understand the principles of that, for that job we're just looking at, you now understand how we do a hotel. You now understand how we do a commercial factory, where we, for example, I won't say the name of the factory, a very, very well-known soft drinks company. They had two air compressors, and they were dumping the heat, and they had problems.
Yeah.
So we took the air compressors, put it into one of the connections on the manifold, connected their existing boiler into the other side, and now they're heating all their offices with their air compressors.
Yeah. It makes the number of times you see people just dumping heat from industrial processes or whatever, and you walk past it and you just feel this heat blowing out from somewhere. Say, surely that could be used. Surely that can be, utilised somewhere.
Laundries.
Yeah.
Laundries, and they're dumping out the heat out the side of the boiler house door, and then they're wondering why the bills are so high with buying fuel to put into the boiler house. It's just shocking.
Yeah, incredible. Well, it's an interesting world you're working in, I think, and it's fantastic to see a little bit of ingenuity spreading across the Atlantic there that way for a change. The brain drain. Great to talk to you, Harry. I'm sure we'll talk again anyway, because I'm fairly convinced that a lot of people are going to find this really interesting, and they're going to have a lot to say about it as well. Put their
and just remember, it's not all for solid fuel. It happens that this particular project we're doing now is solid fuel on it, but the truth of the matter is that the vast amount of time it's just a heat pump or a gas boiler or 2 or 3 gas boilers, because you can also join multiple gas boilers onto a manifold, and then have another manifold with all the zones, so it can be used to collect heat or deliver heat.
Brilliant. What's it called? What do we call this again? This box in the middle?
It's 3 letters, NRG. Just
NRG. And is it yours commercially? Can people buy it from you or what?
absolutely, yeah. And we're trying our damnedest to get merchants in England, but we're finding that it's just, I don't know, maybe it's timing or whatever, but they're really flying in Ireland. We're seriously up the walls. The other thing is that on our website, which is NRG Awareness, you can go and there's a resource tab, and if you put in what boiler you have, it'll give you back a wiring diagram and a pipework diagram to tell you how to do the job. There's about 100 diagrams in there of all different.
That's where I'm going to be spending the rest of my day, looking through that. That's fantastic. Absolutely brilliant. Thank you. Thanks very much for joining us.
Okay.
Let's see you again. Thanks, Harry.
Bye now.